Say we actually want to put an inductance in a circuit. We might actually build ourselves an RL circuit. A circuit element with a large inductance is called an inductor. It looks like this. This would be our symbol in a circuit. And it actually looks just like what it is. It looks like a solenoid type coil. That would be our symbol in the circuit. And such an element would provide a back EMF in such a way that the current in that circuit would not be able to change instantaneously. It's going to make all the current changes more gradual and put less stress on the circuit itself. So imagine we have a series combination of a battery, a resistor, and an inductor with a switch. What's going to happen when I first close the switch? When I first close the switch, the current is going to be changing most rapidly, even though at that moment the back EMF is going to equal the front EMF, and at the moment when I first close the switch, the current is still zero, meaning that the voltage on the resistor at that moment will still be zero as well, because V equals IR, the current being zero, there would be no voltage on the resistance. All the voltage of the battery, when I first close the switch, is going to be found on the inductor itself. So the back EMF would be equal to the forward EMF by the inductance, and hence the net voltage would be zero if you made your way around the circuit. In general, then the voltage of an inductance is equal to the back EMF, and it's equal to negative L di dt. And if we were to apply Kirchhoff's law around the circuit, going around one loop around this series circuit, we would say negative E plus current times resistance plus L di dt equals zero. And that would just be going around the circuit applying Kirchhoff's voltage rule. So we have L divided by R and di dt is equal to the voltage EMF divided by R minus I. L and R are constants, and so we're going to substitute in for L divided by R. Let's just call that tau. Why not? And we're going to substitute in for the voltage divided by R minus I. We're going to make a variable change. We're just going to call that X. It's a constant minus a variable, and so X is going to be equal to that. And so the derivative of X is actually going to be equal to a negative di dt, or vice versa. Negative di dt will equal the derivative of X. So now our equation looks like this. Tau times negative dx dt equals X. Rearranging this equation, I have dx over x is equal to negative 1 over tau, which is a constant, dt. We have two variables. Let's integrate both sides of this equation. And we have natural log of x minus natural log of x naught equals negative 1 over tau times t. This would be natural log of x divided by x naught. And if I take the opposite operation of the natural log, which is the exponent of both sides, I get x divided by x naught is equal to the exponent of negative t over tau. Or x is equal to x naught e to the negative t over tau, where x naught is the voltage divided by resistance, is a constant, and tau is the inductance divided by the resistance, also a constant. Let's replace our expressions for x and x naught in this result. We have the voltage divided by resistance minus I is equal to the voltage divided by resistance e to the negative t over tau. And algebraically simplifying this, we have that the current for all time is the EMF divided by the resistance 1 minus e to the negative t over tau. The voltage divided by the resistance is just the maximum current. So the current is equal to the maximum current 1 minus e to the negative t over tau. And that is our current for all time after we close the switch. Well, let's try it out. If t is equal to 0, what happens? Well, I would have e to the 0 power in this parentheses, and that would be e to the 0, anything to the 0 is going to be 1. So inside the parentheses, I'm going to have 1 minus 1, which indeed is 0. So my current is 0. So right after I close the switch, my current, even at that moment, is still 0. It doesn't change instantaneously. So that's good. What happens if I have the switch closed for a very long time? If the switch is closed for a very long time, t will approach infinity, and e to the negative infinity is, well, if you were to plot e to the negative infinity, it would asymptotically approach 0. And so e to the negative infinity is actually 0. And in the parentheses, I would have 1 minus 0, which is 1. Hence, my current would approach its maximum value, the voltage divided by the resistance. Good. So the current's going to start at 0 and eventually reach its maximum value. Along the way, it's going to be this 1 minus exponential type curve going up. You might see this if you ever set up an LR circuit and feed it a square wave, which is the same as having a switch turned on and off. You will see that there's a leading curve on both ends of your square wave as the current approaches its final value. What happens when t is actually equal to tau? We would have e to the negative tau over tau, or e to the negative 1. And if you ever calculate e to the negative 1 on the calculator, or 1 over e, that is 0.368. And hence 1 minus 0.368 is 0.632. So at that point, the current would equal 0.632 times its maximum value, or 63.2% of its maximum value. If we go up on this curve to 63.2% of the maximum value, it will take us a time equal to this tau, which is equal to L divided by R. We call that the time constant. So by definition, tau is the time constant, is equal to the inductance divided by the resistance, and it is, on this graph, equal to the time it takes for the current to reach 63.2% of its final maximum value. So if I had that kind of curve, I could measure up 63.2%, and I would be able to determine what tau was. Good thing to know. So for a series RL circuit, we can show that the current for all time is our maximum current, 1 minus e to the negative t over tau. The derivative of the current for all time would be the derivative of this. The first term would be the derivative of a constant, which will give us 0. And then if we took the derivative of the exponential, once we decrement or bring down the negative 1 over tau, we will end up with voltage divided by L, e to the negative t over tau. So that is the change in current per time for all time. Hence, the voltage across the resistor by Ohm's law is current times resistance. This first thing, times R, is just going to be the voltage of the battery, 1 minus e to the negative t over tau. And the voltage across the inductance is L di dt. This term times L is just the voltage of the battery, e to the negative t over tau. So that is all of our current, change in current, voltage across the resistor, and voltage across the inductor for all time, where tau is equal to L divided by R. Let's try this out. Here we have a LR series circuit. The switch is closed at t equals 0. First thing, let's find the time constant of the circuit. We don't even have to close the switch to find the time constant. We would know what that is even before we started this circuit, because it is equal to L divided by R. So 30 millihenries divided by 6 ohms gives us 5 milliseconds. So we know that in 5 milliseconds, the current will reach 63.2% of its final value. When doing these problems, it's always good to know, if you can do it, to calculate the time constant, L divided by R, and the maximum current, EMF divided by R, because those are very useful to know for your calculations. What is the current in the circuit? The current for all time is going to be equal to the maximum current, 1 minus e to the negative t over tau. The maximum current is going to be 12 volts divided by 6 ohms, or 2 amps. 1 minus e to the negative t, we just determined tau was 5 milliseconds. 1 over 0.005 is going to be equal to 200. And so this current is going to be 2 amps, 1 minus e to the negative 200 t. That is our current for all time once we close the switch. So for the particular time of t equal to 2 milliseconds, the current would be equal to 2 times 1 minus e to the negative 200 times 2 milliseconds, 0.002, and that would be e to the negative 0.4, and we would get 0.659 amps for the current after 2 milliseconds. We haven't quite made it to the time constant yet. Time constant is 5 milliseconds, so we haven't made it to 63.2% of the final 2 amp current yet. Calculate the current in the circuit and the voltage across the resistor after one time constant has elapsed. After one time constant, we would have e to the negative tau over tau, or e to the negative 1, and that's going to be 0.368, so 1 minus that will be 0.632. That times 2 will give us 1.26 amps. So after one time constant, we are at 63.2% of the final current, 1.26 amps. Hence, the voltage across the resistor by Ohm's law is the current times the resistance. 1.26 amps times 6 ohms is 7.56 volts. If I want to know the voltage across the inductor at this time, I could simply subtract the voltage across the resistor from the battery, and what's left over is the voltage across the inductor. So since the battery was 12 volts, the voltage across this inductor at this moment would be 4.44 volts. Or I could use that other formula, L di dt, to calculate it, but this is a quicker way. If you know the voltage across the resistor, just subtract it from the battery to get the voltage across the inductor. Let's try another problem. What is the self-induced EMF 0.2 seconds after the switch is closed in this circuit? Again, we want to find the time constant if we can. We need to find either the current or di dt at that time, but first we find the time constant. 7 henries divided by 9 ohms, 0.78 seconds, and I max will be the voltage divided by the resistance, 120 volts divided by 9 ohms, 13.33 amps. So that gives us the current for all time. I max 1 minus e to the negative t over tau, 13.33 amps, 1 minus e to the negative t over 0.78, and that will be our current for all time. At the particular time of 0.2 seconds, our current will be 13.33, 1 minus e to the negative 0.2 over 0.78. If we do that calculation, we get 3.01 amps. So the voltage across the resistor in this case would be current times resistance, 3 amps times 9 ohms, 27.13 volts. And the voltage across the inductor would be the voltage of the battery minus the voltage across the resistor, like we were just talking about. 120 minus 27.13, 92.9 volts. Or we could have used the formula, which is L di dt, or the voltage e to the negative t over tau. 120 volts, e to the negative 0.2 over 0.78. I do that calculation in my head, 92.9 volts. The same. Either way you do it, you get the same result. One more problem. Calculate the resistance in a RL circuit in which L is 2.5 henries and the current increases to 90% of its final value in 3 seconds. Here's our current for all time. Its final value is going to be the voltage divided by the resistance. So, if we go to 90% or 0.9 of our final value, our maximum current, that would be equal to our maximum current, 1 minus e to the negative time, 3 seconds, over tau. We can reverse engineer this formula to figure out what tau is, and once we get that, we'll be able to figure out what the resistance is. So our maximum current cancels out, and we have, rearranging this, 0.1 minus 1 is equal to negative e to the negative 3 over tau, or the natural log of 0.1 is going to equal the natural log of e to the negative 3 over tau, which is negative 3 over tau. So tau is going to equal a negative 3 over the natural log of 0.1. That gives us 1.3 seconds. But tau, by definition, is the inductance over the resistance. So the resistance will equal the inductance divided by tau. And that's going to be 2.5 henries divided by 1.3 seconds, 1.92 ohms. Try your hand at the LR circuits in the problem set. The problem set is very short. I think there's only 4 problems. They're all LR circuits. Try your hand and